Tonight, we're going to turn the search for intelligent life around. For decades, humanity has pointed radio telescopes toward distant stars, hoping that somewhere in the Milky Way, another civilization might reveal itself. But while we have been searching for them, Earth has been revealing itself too. Every powerful radio transmission that escapes our planet travels outward at the speed of light. Some of our strongest planetary radar signals are so powerful that, in theory, technology similar to our own could detect them from thousands of light years away. The signals themselves have not traveled nearly that far yet. They are still spreading through our local neighborhood, reaching new stars with every passing year. And by 2030, that detectable footprint will be larger than it is today. More importantly, radio may not be the only clue. From the right location, another civilization could watch Earth cross in front of its star. It could study our atmosphere. It might eventually recognize industrial chemicals, artificial light, powerful radar, or other signatures that are difficult to explain naturally. So tonight, we're going to ask a very different question from whether intelligent life exists somewhere beyond Earth. If another civilization is already looking in our direction, could it find us by 2030? And perhaps more unsettlingly, could it have found us already? Before we continue, if you enjoy these quiet journeys through space, you can like the video or subscribe to Space Like I'm Sleepy. It helps support the channel and lets us keep exploring questions like this together. Now, let's begin with something scientists have recently tried to measure in a surprisingly direct way. In 2025, a team led by astronomer Sophia Sheikh approached this problem by removing one of its biggest unknowns. Instead of imagining what a civilization thousands or millions of years more advanced than humanity might be capable of seeing, the researchers asked a much narrower question. What could another Earth detect about us? Their study, called Earth Detecting Earth, examined our planet as though it were being observed from somewhere else in the galaxy by a civilization using technology roughly comparable to what humanity possesses today. That limitation is important. There is no need to imagine enormous telescopes surrounding entire stars or some unknown form of communication. The experiment begins with instruments, transmitters, and observing techniques that humans already understand. It also reveals that the phrase, "finding Earth," can mean several very different things. Another observer might first discover only that a planet is here. It could measure a tiny repeated change in the light from our star and infer that a roughly Earth-sized world passes in front of it once every year. With better measurements, it might begin studying the planet itself. Light passing through an atmosphere carries information about the gases inside it. Under favorable conditions, an observer could start asking whether that atmosphere looks chemically unusual, whether liquid water might be possible, or whether biological processes could be affecting its composition. That would still be very different from finding humanity. For most of Earth's history, there was no radio, no radar, no artificial lighting, and no industrial chemistry created by a technological species. The planet could potentially reveal life without revealing anything capable of building machines. Only extremely recently has that changed. Modern Earth now produces what researchers call technosignatures. A technosignature is simply evidence that could indicate the presence of technology. It does not have to be a deliberate message. A powerful radar beam can be a technosignature. So can unusual atmospheric pollution, certain kinds of artificial light, concentrated laser emissions, or other changes that would be difficult to produce naturally. And these clues are not equally easy to see. Some are incredibly faint. detecting artificial lighting comparable to modern cities from another star would be extraordinarily difficult, with technology similar to ours. Other signals are much stronger. Earth's most powerful planetary radar transmissions can concentrate so much energy into narrow beams that the 2025 study estimated they could, under favorable conditions, be detectable with comparable technology from distances measured in thousands of light-years. That does not mean anyone thousands of light-years away has received them. A signal cannot outrun light, and most of our powerful transmissions are only decades old. Their physical reach is still tiny, compared with the roughly 100,000 light-year width of the Milky Way. But it means something important has changed about Earth. A few billion years ago, an observer with sufficiently powerful instruments might have found a small rocky planet whose atmosphere had been altered by life. A few thousand years ago, essentially the same was true. Even 200 years ago, Earth produced no radio signal that could identify an industrial civilization. Today, it does. There is now a growing region around our planet where information produced by human technology has physically arrived. Inside that region are real stars, real planetary systems, and worlds that did not yet possess access to those signals a few decades earlier. The boundary continues moving outward at 1 light-year every year. But before we can ask which of those stars might already have received anything useful, there is a more basic problem to solve. A distant civilization would first have to know that there is a planet here at all. And from several light-years away, Earth would be extraordinarily difficult to see. From several light-years away, Earth would not begin as the familiar blue sphere photographed by astronauts. An observer would not see continents, weather systems, city lights, or the curve of an ocean. At first, Earth might exist only as a tiny measurement buried inside the light of its star. One of the most successful ways astronomers find distant planets is called the transit method. A transit happens when a planet passes directly between its star and the observer. The planet blocks a small amount of starlight during the crossing, causing the star to appear slightly dimmer for a predictable length of time. This is how NASA's Kepler Space Telescope discovered thousands of planets and planet candidates after its launch in March of 2009. Kepler did not normally photograph those planets directly. It watched the brightness of more than 100,000 stars at a time, searching for small dips that returned on regular schedules. Earth would create an especially difficult version of that signal. Our planet is about 12,700 kilometers across. The star it orbits is roughly 109 times wider. From a distant star system positioned along the correct line of sight, Earth crossing in front of our star would reduce its apparent brightness by only about 84 parts per million. That is roughly 0.008%. Imagine measuring the brightness of a lamp and noticing that it becomes less than 1/10,000th dimmer. Then imagine making that measurement across several light-years of space, while the star itself is producing natural variations. That is approximately the scale of the task. The change is tiny, but repetition makes it useful. Earth completes one orbit every 365.25 days. An observer in the right position could therefore see the same small reduction in starlight about once each year. After several transits, the repeating schedule would become difficult to dismiss as a random fluctuation. The timing reveals the planet's orbital period. The amount of light blocked reveals the planet's size relative to its star. The length of the transit helps constrain the shape and orientation of the orbit when combined with information about the star itself. a distant astronomer could begin building a surprisingly detailed picture without ever seeing Earth as a recognizable world. There is another technique that could add more information. A planet and its star actually orbit a shared center of mass. Because a star is so much heavier, its movement is small, but sensitive instruments can measure it. Astronomers call this the radial velocity method. They examine the star's spectrum, which is the pattern produced when its light is separated into individual wavelengths. As the star moves slightly toward the observer, those wavelengths shift in one direction. As it moves away, they shift in the other. This effect comes from the same basic physics that changes the pitch of a passing siren, although astronomers measure changes in light rather than sound. Combining transit measurements with radial velocity can be especially powerful. The transit helps estimate a planet's radius. The gravitational wobble helps estimate its mass. Together, those values can reveal density, which helps distinguish a small, rocky world from something much less like Earth. For an observer studying our system, the result might eventually look something like this. One roughly Earth-sized planet moving around an ordinary star once every year, at a distance of about 1 astronomical unit. An astronomical unit is simply the average distance between Earth and its star, about 150 million kilometers. Even that would leave most of the important story hidden. A planet with Earth's size and orbit does not automatically have oceans. Its atmosphere might be very different from ours. Surface temperature depends on atmospheric pressure, greenhouse gases, clouds, reflectivity, and the amount of energy arriving from the star. A world can occupy what astronomers call the habitable zone, the range of distances where liquid water could potentially exist under suitable conditions while remaining completely lifeless. So finding Earth would initially tell another civilization surprisingly little about what was actually happening here. They might know its approximate size. They might calculate its year. With enough additional measurements, they might estimate its mass and conclude that it was probably rocky. Humanity would still be invisible inside those numbers. And even this first clue would be available only from certain parts of the galaxy, because a transit requires extremely precise alignment. From most stars in the Milky Way, Earth never crosses the face of its star at all. The geometry that makes a transit visible is surprisingly strict. Earth moves around its star in a nearly flat orbital plane. From somewhere close to that plane, our planet can appear to pass directly across the face of the star once each year. Shift the observer far enough above or below that plane, though, and the apparent path changes. Earth still completes the same orbit, but it passes beside the stellar disk instead of across it. That means only a relatively narrow band of locations in space can use the transit method to discover Earth. Astronomers call this region the Earth Transit Zone. From inside that zone, an observer with sufficiently sensitive instruments could watch the brightness of our star fall by about 84 parts per million during an Earth transit. From most other directions, that particular signal never occurs. The idea becomes especially useful when astronomers combine it with measurements of how nearby stars move. In 2021, astronomers Lisa Kaltenegger and Jackie Faherty used data from the European Space Agency's Gaia mission to reconstruct which nearby stars have occupied this viewing zone over a period spanning 10,000 years. Gaia is a space observatory designed to map the positions and motions of stars with extraordinary precision. Launched in 2013, it has measured well over 1 billion stars across the Milky Way. For nearby stars, those measurements allow astronomers to do more than locate them today. They can estimate where those stars were thousands of years ago and where their motion will carry them in the future. Kaltenegger and Faherty examined stars within about 100 parsecs of Earth. A parsec is a unit astronomers use for stellar distances. 1 parsec equals roughly 3.26 light-years. So 100 parsecs works out to about 326 light-years. Within that distance, they identified 1,715 stars that had been positioned to see Earth transit during the roughly 5,000 years associated with the rise of early human civilization. Another 319 stars are expected to enter the correct geometry during the following 5,000 years. Those numbers help show why the sky should not be treated as a set of permanently fixed viewing positions. Every star is moving. Our own star travels around the center of the Milky Way at hundreds of thousands of kilometers per hour. Nearby stars follow their own galactic paths. Their positions relative to Earth therefore change slowly over centuries and millennia. A system that can see Earth transit today may eventually lose that alignment. Another system that cannot see the transit now may drift into the correct position later. Ross 128 provides a real example. Ross 128 is a red dwarf about 11 light-years from Earth. Astronomers know that at least one planet orbits it. The system was positioned to see Earth transits beginning roughly 3,000 years ago, but it moved out of that viewing geometry around 900 years ago. So if an observer there had been watching during that period, Earth could have appeared as a small repeating dip in the light from our star. Teegarden's star, another nearby red dwarf, lies about 12.5 light-years away. Its changing position is expected to bring it into the Earth transit zone on a much shorter future timescale. TRAPPIST-1 is farther away, at roughly 40 light-years. It is famous because 7 roughly Earth-sized planets have been found around the star. According to the same study, observers in that system would begin seeing Earth transits in about 1,600 years. None of these examples should be treated as evidence that intelligent life exists there. The significance is geometric. Ross 128 does not become more likely to host a civilization because it once had a good view of Earth. TRAPPIST-1 does not become more likely to contain observers because it will gain that view in the future. These systems simply demonstrate that some locations offer a much more useful line of sight toward our planet. That distinction matters because the ability to find Earth depends on more than distance. An observer could be relatively nearby and completely miss the transit signal because the orbital plane is tilted from its point of view. Another observer farther away could have almost perfect alignment and watch the same small dip repeat year after year. And even the best possible alignment would reveal only that a planet is there. Earth had been carrying a much older clue for billions of years before human technology ever appeared. For most of Earth's history, the most revealing information about the planet would have come from its atmosphere rather than anything built on the surface. Earth formed about 4.54 billion years ago from rock and metal accumulating around the young star at the center of our solar system. The early planet was hotter and far more violent than the world we know today. Large impacts were common. Volcanic activity released gases from the interior, and the atmosphere changed repeatedly as the surface cooled. Evidence for life appears surprisingly early in that history. Some of the oldest widely accepted signs of biology are at least 3.5 billion years old. Tiny organisms were already living on a planet that was still relatively young. For billions of years afterward, however, an observer studying Earth would have found nothing resembling technological civilization. There were no radio transmitters. There were no artificial satellites. Industrial chemicals were absent because industry itself did not exist. Biology was already changing the planet in ways that could eventually become visible from far away. Among the most important organisms were early photosynthetic microbes, including ancestors of modern cyanobacteria. Photosynthesis uses light energy to build organic molecules. In the form practiced by cyanobacteria, water is part of that process, and oxygen is released as a byproduct. At first, much of this oxygen did not remain in the atmosphere. It reacted with iron dissolved in ancient oceans and with exposed minerals on the surface. Evidence of that chemistry survives in banded iron formations, rocks containing alternating iron-rich layers that can be more than 2 billion years old. Eventually, oxygen production began outrunning some of these chemical sinks. Around 2.4 billion years ago, Earth entered what geologists call the Great Oxidation Event. Atmospheric oxygen rose substantially compared with earlier conditions. The exact concentrations changed over time, but the transition permanently altered Earth's surface environment. As oxygen accumulated higher in the atmosphere, some of it formed ozone. Ozone consists of 3 oxygen atoms joined together. Its layer in the upper atmosphere absorbs much of the star's damaging ultraviolet radiation, providing additional protection for organisms living near the surface. A distant observer would not need to collect a sample of Earth's air to investigate these gases. Astronomers use a technique called spectroscopy. When light is separated into its individual wavelengths, it forms a spectrum. Different atoms and molecules interact with particular wavelengths in recognizable ways. Oxygen absorbs light at certain wavelengths. Water vapor has another pattern. Methane and carbon dioxide leave their own sets of features. During a planetary transit, a small amount of starlight can pass through the thin outer edge of a planet's atmosphere before reaching a distant telescope. Some wavelengths are absorbed more strongly than others. With sufficiently sensitive instruments and enough repeated observations, those differences can reveal which gases are present. Scientists call a potentially biological clue detected this way a biosignature. A biosignature deserves careful interpretation because nature can produce misleading results. Oxygen is an important example. Living organisms generate most of the oxygen in Earth's modern atmosphere, but certain non-biological chemical processes can also produce oxygen under particular planetary conditions. Combinations of gases can therefore be more informative than one molecule alone. Modern Earth contains both oxygen and methane. That pairing is interesting because the two gases react chemically. In today's oxygen-rich atmosphere, an individual methane molecule typically survives only around a decade before chemical reactions destroy it. Yet methane remains present because new methane continually enters the atmosphere. On Earth, major sources include microorganisms called methanogens, which live in oxygen-poor environments, such as wetlands and sediments. Geological processes and modern human activity contribute as well. If a distant planet showed substantial quantities of gases that should steadily react away, an astronomer could begin asking what process keeps replacing them. This condition is known as chemical disequilibrium. It means an atmosphere contains a combination of substances that would move toward a different chemical balance unless something continuously replenished them. A sufficiently capable observer studying ancient Earth might therefore have found a planet whose atmosphere behaved in ways consistent with ongoing biology long before animals appeared on land. That possibility stretches across an enormous portion of Earth's history. Modern humans have existed for only about 300,000 years. Radio technology has existed for little more than a century. Against 4.5 billion years of planetary history, the technological period is almost vanishingly short. Then, within only a few human generations, Earth acquired an entirely new set of signals. The change began only a little more than a century ago. In 1887 and 1888, German physicist Heinrich Hertz carried out experiments that proved electromagnetic waves could be produced and detected in the laboratory. He created sparks across a small gap, generated radio waves, and detected them across the room with another loop of wire. At the time, this was a physics experiment rather than a communication system. Within a few years, that changed. Guglielmo Marconi began developing practical wireless telegraphy in the 1890s. In 1895, he successfully sent wireless signals over distances of more than a kilometer in Italy. By 1901, his company transmitted a radio signal across the Atlantic Ocean, from Cornwall in England to Newfoundland in Canada. For the first time in Earth's history, machines were deliberately sending information through the atmosphere without a wire connecting the transmitter and receiver. Early systems used radio mainly for telegraphy. Operators sent coded pulses, often using Morse code, between ships and coastal stations. During the first decades of the 20th century, radio equipment became more powerful, more reliable, and much more widespread. Broadcasting expanded rapidly during the 1920s. Stations began transmitting speech and music to large audiences rather than communicating with a single receiver. In the United States, Pittsburgh station KDKA is often associated with one of the earliest commercial radio broadcasts in 1920. Within only a few years, hundreds of stations were operating across North America and Europe. Those transmitters were designed to cover cities, regions, and sometimes entire countries. Most of their energy remained useful near Earth, but radio waves do not stop at the edge of the atmosphere. Any portion directed upward can continue into space. Television added more transmitters during the following decades. Experimental television systems existed before the Second World War, and commercial broadcasting expanded dramatically after 1945. Large antennas sent increasingly powerful signals across wide areas. By then, Earth had begun producing a technological electromagnetic background that had never existed during the previous 4.5 billion years of planetary history. Radar created a different kind of signal. Radar works by transmitting radio waves toward an object and measuring the faint echo that returns. Development accelerated during the 1930s, and radar became critically important during the Second World War for detecting aircraft and ships. The important difference is concentration. A broadcast transmitter may spread energy over a broad region, so many receivers can pick it up. Radar systems often direct much more of their energy into a narrower beam. That can make the signal far more intense along the direction in which the antenna is pointed. After the war, radar began reaching beyond Earth. In 1946, the United States Army Signal Corps conducted Project Diana from New Jersey and successfully bounced radar signals off the moon. The round trip took about 2.5 seconds. That experiment demonstrated that human radio technology could deliberately illuminate an object hundreds of thousands of kilometers away and detect the returning echo. Planetary radar soon went farther. During the 1960s and later decades, facilities including the Arecibo Observatory in Puerto Rico and the Goldstone Solar System radar in California transmitted powerful beams toward planets, moons, and near-Earth asteroids. The returning signals allowed astronomers to measure distances, rotation rates, and surface properties with remarkable precision. Space exploration added another source of outward radio traffic. When spacecraft began traveling toward the Moon and planets, communication systems on Earth had to send narrow beams across millions of kilometers. NASA's Deep Space Network grew from tracking stations created around the beginning of the space age. Its large antennas in California, Spain, and Australia communicate with spacecraft throughout the solar system. A transmission intended for a spacecraft near Mars does not simply vanish after reaching it. The radio energy continues beyond the target. The same is true for radar pulses and other transmissions that escape Earth. Once electromagnetic radiation is moving freely through space, it travels at the speed of light, about 300,000 kilometers every second. In 1 year, it crosses 1 light year. A transmission sent 50 years ago has therefore had time to move about 50 light years from Earth. A signal sent 100 years ago has reached roughly 100 light years, assuming nothing blocks or absorbs it along the way. This creates an intuitive picture of humanity inside a growing radio bubble, with older emissions farther out and newer ones closer to home. That picture is useful for understanding travel time. It becomes much less reliable when we ask whether anyone inside that bubble could actually detect what Earth sent. The distance a radio wave has traveled tells us almost nothing by itself about whether someone could recognize it. Consider a signal transmitted from Earth in 1895. By 2030, the oldest part of that transmission could be roughly 135 light-years away. Hundreds of star systems lie inside a sphere that large. It is easy to imagine that any sufficiently advanced listener inside that region could simply tune a receiver toward Earth and hear the beginnings of human radio. The physics is much less generous. As radio energy moves outward, it spreads across an increasingly large area. For a transmitter radiating roughly equally in every direction, the same amount of energy that once occupied a relatively small region eventually becomes distributed across the surface of an enormous sphere. The surface area grows with the square of the distance. This produces the inverse square law. If an observer moves twice as far from the transmitter, the received power per unit area falls to 1/4. At 10 times the distance, it falls to about 1/100th. At 100 times the distance, it falls to about 1/10,000th. A radio wave does not suddenly disappear when it becomes weak. Its energy continues moving through space. The problem is that eventually the signal becomes so faint that a receiver can no longer distinguish it from everything else arriving at the antenna. And space contains plenty of radio energy. Stars produce radio emission. Charged particles moving through magnetic fields generate it. The gas between stars contributes noise at some frequencies. Distant galaxies contain radio sources powerful enough to be detected across millions or billions of light years. Pulsars add another example. These rapidly rotating neutron stars can produce extremely regular radio pulses. When pulsars were first discovered in 1967, their unusual regularity was so striking that researchers briefly considered whether an artificial source needed to be ruled out. Closer to Earth, the problem becomes even messier. Satellites, aircraft systems, navigation transmitters, mobile networks, radar installations, and countless other technologies fill parts of the radio spectrum with human-made interference. An observer trying to detect technology on Earth would therefore need more than a radio telescope. It would need enough signal compared with the surrounding noise. Astronomers describe this using the signal-to-noise ratio. A strong signal standing well above the background is comparatively easy to identify. A weak signal buried among natural and artificial radio sources may require repeated observations, long periods of measurement, or a much larger receiving antenna. The frequency range occupied by the transmission matters too. A radio broadcast designed to carry speech or television uses a band of frequencies. Its energy is spread across that band. A very narrow signal concentrates its energy into a much smaller frequency range. That concentration can make it easier to identify, because the receiver can examine a tiny slice of the spectrum and accumulate energy there while rejecting much of the surrounding noise. Time matters as well. If a telescope knows where to look and the source remains stable, it can collect radio energy for seconds, minutes, or hours. Combining those measurements can reveal signals too faint to notice instantly. A civilization trying to detect Earth would therefore care about transmitter power, frequency, bandwidth, observing time, receiving antenna size, and the direction in which the energy was sent. Geometry can change the result enormously. This gives us two separate boundaries around Earth. The first is the propagation horizon. That is simply the maximum distance a particular signal could have physically reached. A transmission sent 70 years ago cannot be more than about 70 light-years away. The second is the detection horizon. That is the distance at which a particular observer, using a particular instrument, could still recognize that transmission as something distinct from background noise. A signal can have a propagation horizon of 100 light-years while becoming effectively undetectable long before reaching most of that volume. Another signal can remain detectable across enormous distances but occupy only a narrow beam that almost nobody happens to cross. So the radio environment surrounding Earth is much more complicated than a glowing sphere announcing humanity to every nearby star. Most ordinary leakage becomes extremely faint. A much smaller class of human transmissions behaves very differently, because instead of spreading their power broadly across the sky, they concentrate enormous amounts of radio energy into a narrow direction. The strongest technological radio signature Earth has produced comes from a very different use of radio. A broadcast station is designed to cover a wide region. Its signal spreads across cities and surrounding countryside so that many receivers can pick it up. Planetary radar works differently. It concentrates a large amount of radio energy into a narrow beam and points that beam toward a specific object in space. That concentration produces what engineers call antenna gain. A large dish does not create extra energy. It redirects more of the available energy into a preferred direction. From somewhere inside the main beam, the transmitter can therefore appear enormously more powerful than the same equipment radiating equally across the sky. For decades, one of the clearest examples stood in a natural limestone depression near Arecibo, Puerto Rico. The Arecibo Observatory's main reflector measured about 305 meters across. Completed in 1963, it became one of the world's most recognizable radio telescopes. The same enormous dish that received faint radio waves from space could also be used as part of a powerful planetary radar system. Astronomers transmitted radio energy toward objects in the solar system and then waited for a tiny fraction of that energy to reflect back. A radar pulse sent toward the Moon can return in roughly 2.5 seconds. Venus is much farther away, so the round-trip time varies by many minutes, depending on where the planets are in their orbits. Near-Earth asteroids can be tracked by measuring the delay and frequency shift of their radar echoes. Those echoes reveal information that an ordinary photograph may not provide. Radar observations can measure an asteroid's distance with great precision, refine its orbit, estimate its rotation rate, and sometimes produce coarse images of its shape. This has been especially useful for near-Earth objects, whose future trajectories need to be calculated carefully. The outgoing transmission required to perform those measurements was extraordinarily intense along the direction in which Arecibo was pointed. That matters when Earth is considered from another star. In 2025, Sophia Sheikh and her colleagues compared several kinds of technological evidence produced by modern Earth. They asked how far away each signal could theoretically be detected if the observer possessed receiving technology broadly comparable to ours. Planetary radar dominated the comparison. Under the assumptions used in the study, an Arecibo-like planetary radar transmission could potentially be detectable from approximately 12,000 light-years away if an observer happened to lie within the beam and had suitable receiving equipment. That distance is difficult to reconcile with the faint image of Earth we built in the previous section. The nearest star system is only about 4.24 light-years away. Sirius is roughly 8.6 light-years away. The center of the Milky Way lies about 26,000 light-years from Earth. A 12,000 light-year detection range would therefore extend far beyond the small neighborhood containing the stars visible around us on a local map. It would reach through a substantial portion of the galactic disk. The result also shows how misleading ordinary broadcast leakage can be as the standard example of Earth's radio presence. Television and commercial radio distribute their power relatively broadly and were built for receivers on or near Earth. Planetary radar was designed to send a concentrated signal across millions of kilometers and still recover an echo after only a tiny fraction returned. A distant receiver located in the correct direction would see that difference immediately. But the 12,000 light-year figure describes potential detectability under favorable conditions. It does not describe an enormous region that has already been exposed to Arecibo's strongest radar. The beam occupied only a small portion of the sky at any moment. It followed specific planets, asteroids, and other targets. Most directions never received the strongest part of a particular transmission. The transmissions were also intermittent. Planetary radar did not illuminate the galaxy continuously. Arecibo itself stopped operating after severe cable failures in 2020. On December 1st of that year, its suspended instrument platform collapsed into the dish, ending more than half a century of observations at the site. So, Earth's loudest technological signature behaves less like a lighthouse shining in every direction and more like a narrow searchlight that appeared at particular times and swept across selected paths. Someone positioned directly inside one of those paths could receive a remarkably conspicuous signal. Someone at the same distance in another direction might receive nothing comparable at all. And there is an even more important limitation hiding inside that 12,000 light-year number. Radio can be powerful enough to cross an enormous distance, but the information still cannot arrive before light has had enough time to travel there. The 12,000 light-year figure describes how far away an Arecibo-like signal might remain detectable under favorable conditions. It does not describe how far that signal has actually traveled. Radio waves move at the speed of light, about 300,000 kilometers every second. A light year is simply the distance light travels in 1 year, roughly 9.46 trillion kilometers. That gives every transmission a strict historical boundary. If a signal left Earth 10 years ago, it cannot be more than 10 light-years away today. A receiver 20 light-years away has not received it yet, regardless of how sensitive that receiver might be. The same rule applies to Earth's strongest radar. An Arecibo-like transmission might theoretically remain recognizable across 12,000 light-years, but reaching an observer 12,000 light-years away would require 12,000 years of travel. Humanity has not been producing planetary radar for anything close to that length of time. This becomes easier to picture when we assign dates to different layers of Earth's radio history. Take 1895, when Guglielmo Marconi was carrying out some of his earliest successful wireless experiments. By 2030, any electromagnetic radiation that escaped Earth during that year will have had about 135 years to travel. Its outermost possible wavefront will therefore be about 135 light-years away. That is the largest historical radius available to the earliest human radio experiments. Now move forward to 1960. That year is especially useful as a rough marker for the beginning of modern systematic searches for extraterrestrial radio signals. Frank Drake conducted Project Ozma at the Green Bank Observatory in West Virginia, listening toward Tau Ceti and Epsilon Eridani. A signal leaving Earth in 1960 reaches about 70 light-years by 2030. Move forward again to 1974. On November 16th of that year, the Arecibo Observatory transmitted its famous interstellar message toward the globular cluster Messier 13. The message contained 1,679 binary digits. It was sent at a frequency near 2,380 MHz and lasted less than 3 minutes. By 2030, that transmission will have traveled only about 56 light-years from Earth. Messier 13 sits roughly 25,000 light-years away, so the message still has almost its entire journey ahead of it. These examples reveal something important about Earth's electromagnetic history. The oldest signals have traveled the farthest, but they are not necessarily the easiest to detect. Early wireless experiments were comparatively weak. Later, broadcasting became stronger. High-power radar introduced much more intense directional emissions, but those systems appeared decades after Marconi. A faint signal from 1895 can therefore be physically farther from Earth than a much stronger radar pulse transmitted in 1980. The stronger transmission may have a much larger theoretical detection range, while occupying a smaller actual region of space because it has had less time to travel. Humanity's radio presence is better imagined as many overlapping layers. Some emissions spread broadly and have been traveling for more than a century. Other transmissions form narrow beams aimed toward planets, asteroids, or spacecraft. Each beam begins on a particular date, travels in a particular direction, and carries a particular amount of power. That makes the space around Earth uneven. One star 70 light-years away may already lie inside the historical reach of certain 1960-era emissions. Another star at the same distance may never have crossed the strongest part of a later radar beam. A system 50 light-years away could already have been reached by a 1970s transmission, while a system 100 light-years away still lies beyond every signal produced during the modern radar era. 2030, therefore, marks no sudden physical threshold. It advances every existing electromagnetic wavefront by 4 light-years compared with 2026. The oldest human radio emissions move from roughly 131 light-years to roughly 135. A 1960 signal moves from about 66 to 70 light-years. The 1974 Arecibo message moves from about 52 to 56. That steady expansion gives the date meaning without requiring anything dramatic to happen during that particular year. Earth's detectable history is simply continuing to move outward. And once signal strength and travel time are separated, distance alone stops being enough. Direction becomes just as important, because Earth's most powerful transmissions were never sent evenly across the sky. A powerful transmission can be intense in one direction and almost irrelevant in another. That happens because radio antennas do not send energy through space in perfectly uniform spheres. The shape of the radiation depends on the antenna, the frequency, and the way the transmitter is being used. Ordinary broadcast leakage tends to cover a broad region. A radio station wants many receivers spread across a city or countryside to hear the same program, so its antenna is designed for wide coverage. Deep space communication and planetary radar have a different job. A large dish concentrates much more of its energy into what engineers call the main beam. This is the central, strongest part of the radio pattern, aimed toward a specific target. Beam width depends partly on the size of the dish and the wavelength of the signal. In general, a larger antenna produces a narrower beam at the same wavelength. Shorter wavelengths can narrow the beam further. That narrower pattern concentrates the available energy. The trade-off is coverage. A broad transmission illuminates more sky at lower intensity. A narrow beam can become dramatically easier to detect along its path while crossing only a small portion of the sky. This is one reason a facility like Arecibo could produce such an extraordinary theoretical detection range. Its enormous 305-meter reflector could direct a powerful radar transmission toward a particular asteroid or planet. A receiver located somewhere along that line would experience a much stronger signal than another receiver positioned the same distance from Earth but well outside the beam. The beam also does not remain fixed against the stars. Suppose astronomers are tracking a near-Earth asteroid. The asteroid is moving around the star at the center of the solar system. Earth itself is moving through its orbit. The observatory rotates with Earth once every day. The radar antenna must continually adjust its pointing direction to keep the target inside the beam. A distant star lying behind the asteroid from Earth's point of view could briefly fall near that transmission path. As the geometry changes, the beam moves away. The same principle applies to communication with spacecraft. A deep space antenna sending instructions to a probe near Mars must follow the spacecraft across the sky. Hours later, Earth's rotation has changed the antenna's orientation. Days later, the relative positions of Earth, Mars, and the spacecraft have shifted again. So a distant observer might encounter a strong human transmission for a limited period and then hear nothing comparable afterward. The silence that follows would not necessarily mean the transmitter had disappeared. The beam may simply have moved. Real antennas make the situation slightly more complicated. A dish does not produce one perfectly clean pencil of radio energy. Smaller amounts of power escape into weaker regions called side lobes. These appear at angles away from the main beam because radio waves interfere with one another as they leave the antenna structure. Side lobes matter for radio engineering and can sometimes create interference in directions the transmitter was not intentionally targeting. For interstellar detectability, though, the main beam remains far more important because it carries the greatest concentration of power. This changes the picture of Earth's radio presence once again. Instead of a smooth sphere expanding evenly through the galaxy, modern Earth produces a complicated pattern of overlapping emissions. Weak broadcast leakage spreads broadly. Powerful radar forms narrow paths. Deep space communication creates additional beams that follow spacecraft and planets across changing directions. Two hypothetical civilizations could sit 20 light-years from Earth and receive very different evidence of us. One might happen to lie near the path of a powerful radar transmission and see a conspicuous artificial signal. Another, at the same distance, could remain outside those strongest beams and receive only much weaker leakage. Distance alone cannot tell us who has been exposed to Earth's technology. Timing and direction now matter just as much. Fortunately, Some of humanity's most important transmissions were recorded in enough detail that their directions can be reconstructed. NASA's deep space communication logs provide one of the clearest examples, covering years of transmissions aimed across the solar system. NASA's Deep Space Network gives us a much more precise map of where some of Earth's strongest communication beams have actually gone. The network consists of 3 major communication complexes spaced around the planet. One is at Goldstone, in California's Mojave Desert. Another is near Madrid, Spain. The third is near Canberra, Australia. Their locations are separated by roughly 1/3 of Earth's circumference. That spacing matters because Earth rotates once every 24 hours. As a spacecraft drops below the horizon from one site, another site can often take over communication. This allows NASA to maintain contact with missions traveling far beyond Earth for much of the day. The antennas themselves are enormous. Each complex includes dishes tens of meters across, including 70-meter antennas designed to receive extremely weak signals from distant spacecraft. The same network can send commands outward, using tightly directed radio beams. Those uplinks have supported missions around Mars, spacecraft near Jupiter, probes crossing the outer solar system, and vehicles traveling far beyond the planets. Voyager 1 provides an extreme example. It is now more than 20 billion kilometers from Earth, yet Deep Space Network antennas can still exchange radio signals with the spacecraft. A transmission sent toward a probe does not stop when it reaches the probe. Most of the radio energy continues beyond it, along approximately the same direction. The spacecraft intercepts only a tiny fraction of the beam. That means a civilization located farther along the same line could, under suitable conditions, receive some of the energy humans sent toward our own machines. This idea became much more concrete in 2025. Researchers Pinshen Fan, Jason Wright, and T. Joseph Lazio examined roughly 20 years of NASA Deep Space Network uplink records. Instead of treating Earth's radio leakage as random, they reconstructed where those transmissions were pointed and how often particular parts of the sky were illuminated. The pattern was strongly structured. A large fraction of deep space traffic naturally follows directions near what astronomers call the ecliptic. The ecliptic is the plane defined by Earth's orbit. Most of the major planets orbit fairly close to that same plane. So spacecraft traveling to Mars, Jupiter, or other planets spend much of their time in directions clustered around it. Deep space transmissions therefore concentrate radio energy toward particular regions of the sky more often than toward others. Some beams are directed approximately toward the inner solar system. Others point outward toward spacecraft beyond Earth. Planetary alignments change the exact directions over months and years, but the overall pattern remains linked to the geometry of our planetary system. The researchers then compared these directions with the Earth transit zone we discussed earlier. That overlap produced a striking result. The average Deep Space Network transmission duty cycle inside the Earth transit zone was about 20 times higher than the average across ecliptic latitudes more generally. Duty cycle simply means the fraction of time a transmitter is active toward a particular direction. So, a hypothetical observer sitting in the narrow region where Earth crosses the face of its star could also have an unusually good chance of lying near directions repeatedly illuminated by our deep space communication. The geometry becomes even more concentrated during certain planetary alignments. The study examined Earth and Mars when the two planets appear close together in the sky from a distant observer's perspective. During these conjunctions, communication beams associated with Mars missions become especially predictable. Across the approximately 20 years of transmission records they analyzed, the researchers calculated that a properly positioned observer monitoring during these Earth-Mars conjunctions would have had about a 77% chance of observing, while a deep space network transmission was occurring, compared with choosing a completely random direction and a completely random time. That represented roughly a 400,000-fold improvement in the chance of catching one of those transmissions. The number does not mean anyone was there listening. It shows that human radioactivity has structure. A distant astronomer who understood that Earth had planets could potentially use planetary geometry to decide when and where to listen more carefully. Our exploration of the solar system has created regular patterns in the radio sky, and some real nearby stars occupy especially interesting positions within those patterns because they have also had the geometry needed to watch Earth pass across its star. Among the nearby systems identified in the Earth Transit Zone study, some occupy an especially interesting overlap between geometry and history. Lisa Kaltenegger and Jackie Faherty did more than reconstruct which stars could see Earth pass across the face of its star. They also compared those viewing positions with the expanding reach of human radio transmissions. When their study was published in 2021, human-made radio waves had already passed 75 of the closest stars in their Earth Transit Zone sample. That does not mean those 75 stars received a clear broadcast from humanity. Many early transmissions would have been extremely weak by the time they arrived. The result establishes something more basic and more useful. Those systems had both the right viewing history to discover Earth through transits, and enough proximity for at least some human radio emissions to have physically reached them. Ross 128 is a good example. It is a small red dwarf in the constellation Virgo, roughly 11 light-years from Earth. The star is much cooler and dimmer than the one Earth orbits, with only a fraction of its mass. In 2017, astronomers announced the discovery of a planet called Ross 128b, orbiting it. The planet completes an orbit in about 9.9 days and has a minimum mass a little greater than Earth's. Its actual surface conditions remain unknown, and nothing about the planet provides evidence for life or technology. Ross 128 matters here because of its position. For a period beginning roughly 3,000 years ago, the system lay inside the narrow region from which an observer could watch Earth transit. It moved out of that geometry around 900 years ago as the stars continued along their paths through the Milky Way. Imagine, purely as a scientific exercise, that astronomers had existed there during that viewing period. Earth might first have appeared as a tiny recurring reduction in the brightness of a distant star. The event would return approximately once every 365 days. Repeated measurements could reveal the orbital period. Transit depth could show that the planet was roughly terrestrial in size. With enough additional observations, the system's astronomers might estimate the planet's mass and determine that it was probably rocky. Atmospheric measurements would require much more capable instruments. If those became available, they could begin searching the thin layer of gas surrounding Earth for water vapor, oxygen, methane, or other molecules. Depending on the technology available and the era of Earth being observed, those measurements might make the planet biologically interesting. Human technology would arrive as a later chapter. Radio signals leaving Earth do not appear at Ross 128 immediately when humans transmit them. The system is roughly 11 light-years away. So every piece of electromagnetic information requires about 11 years to cross the distance. An observer there looking toward Earth during 2026 would therefore receive light and radio information describing Earth around 2015. A transmission sent from Earth in 1960 would reach Ross 128 around 1971. A transmission sent in 1974 would arrive around 1985, provided energy from that particular emission traveled in its direction and remained detectable. This delay applies to everything that can be observed remotely. The distant planet seen through a telescope is always an earlier version of itself. A star 50 light-years away appears as it was 50 years ago. A galaxy 2 million light-years away is observed more than 2 million years in its past. For nearby systems, the delays are short enough to fit within human history. That allows several independent clues about Earth to arrive at different times. A planet could be known long before the first useful technological emission reached the same observer. Biological evidence could be studied for generations before a sufficiently strong artificial signal appeared. The observer would not need to learn everything about Earth at once. Its understanding could accumulate gradually as new information crossed the intervening light years. And once a system lies only a few tens of light years away, the calendar allows something even more interesting. There may already have been enough time for information to travel from Earth, be received elsewhere, and for a response traveling at light speed to begin the journey back. At a distance of 10 light years, the timing becomes simple enough to follow almost like a clock. A radio signal leaving Earth requires 10 years to cross 10 light-years. If a civilization at that distance detected the signal and responded immediately, its reply would need another 10 years to return. The absolute fastest possible round trip would therefore take 20 years. That is a lower limit set by the speed of light. Real communication would almost certainly take longer. A receiver would need to notice the signal, decide that it was artificial, determine where it came from, and choose whether to answer. Even a delay of a few months or years would push the return date later. Still, the light travel limit gives us a useful way to measure what is physically possible. Suppose Earth sends a signal in a particular year, and we ask whether a reply could arrive by 2030. First, count the number of years between the transmission and 2030. Then divide that number by 2. The result is the maximum distance in light years, from which an immediate light speed response could make the complete round trip in time. Take 1960. 70 years, separate 1960 from 2030. A signal transmitted that year could spend 35 years traveling outward, and an immediate response could spend another 35 years traveling back. That creates an idealized round-trip limit of about 35 light-years. Any hypothetical observer located within that distance could, in principle, receive a 1960 transmission and return an electromagnetic response that reaches Earth by 2030. At 35 light-years exactly, the timing would be extremely tight. The original signal would arrive around 1995. A response sent immediately would reach Earth around 2030. At 20 light-years, the schedule is more generous. A 1960 signal would arrive around 1980. An immediate reply could return around the year 2000. At 10 light-years, the same exchange could be completed by 1980. The date of the original transmission changes the boundary. In 1974, the Arecibo Observatory sent its famous interstellar message toward the globular cluster Messier 13. 56 years separate 1974 from 2030. Half of 56 is 28. So a hypothetical observer, no farther than about 28 light-years away, could, under the most optimistic possible timing, receive a 1974 signal, and return a light-speed reply by 2030. At 28 light-years, the outbound message would arrive around 2002. An immediate response would then require another 28 years to reach Earth. These calculations say nothing about whether a civilization actually exists within 35 light-years. They also do not tell us whether an old human transmission remained strong enough to detect at that distance, whether its beam crossed the correct system, or whether anyone happened to be observing at the right moment. The calculation describes only the boundary allowed by light travel. That distinction is important because it changes the meaning of the word already. For distant parts of the Milky Way, humanity's technological history has not arrived yet. A civilization hundreds of light years away would still be seeing Earth from before modern radio existed. Within a few tens of light years, the timeline is different. There has been enough time for certain human signals to reach nearby systems. In the closest cases, enough additional time has also passed for information traveling at light speed to come back. That does not mean a reply is on its way. It means the universe no longer forbids one on timing grounds alone. Radio, however, remains dependent on brief transmissions, narrow beams, and fortunate observing geometry. A civilization studying Earth over long periods could also search for clues that remain written into the planet itself. Some technological evidence could remain visible even when no radio beam happened to pass nearby. The same spectroscopy used to search an atmosphere for signs of biology can also be applied to chemicals associated with industry. Instead of looking only for gases such as oxygen, methane, or water vapor, an observer could search for compounds whose abundance or distribution might be difficult to explain without technological activity. One example is nitrogen dioxide. Nitrogen dioxide is a reddish-brown gas made of nitrogen and oxygen. On modern Earth, it is produced by several natural processes, including lightning and some forms of soil chemistry. Human activity adds a major additional source. Whenever fuel burns at high temperature, nitrogen and oxygen in the air can react to form nitrogen oxides. Cars, trucks, power stations, factories, and other combustion systems therefore release these compounds into the atmosphere. Nitrogen dioxide is familiar to atmospheric scientists because it contributes to urban air pollution and the formation of smog. From another star system, no observer would see a traffic jam or a smokestack directly. The possible clue would instead be written into the spectrum of Earth's atmosphere. During a transit, a small fraction of light from our star passes through the thin outer edge of Earth's atmosphere before continuing toward the observer. Astronomers sometimes call this atmospheric limb, the narrow region around the edge of a planet, where the line of sight passes through a relatively long column of gas. Molecules in that gas absorb particular wavelengths. If an instrument measures the spectrum carefully enough, it can search for the characteristic absorption pattern associated with a molecule such as nitrogen dioxide. The signal would be extremely faint. Earth's atmosphere forms only a thin shell around a planet nearly 12,700 kilometers wide. A distant telescope would be trying to isolate the effect of specific molecules inside that thin layer, while most of the light still comes directly from the much larger star behind it. Repeated transits can help. Earth crosses its star once each year from the correct viewing geometry. An observer could collect measurements during one transit, return the following year, and combine many observations to improve the signal-to-noise ratio. This is one reason atmospheric technosignatures are interesting. They can persist for much longer than a brief radio transmission. A radar beam might cross a distant system for minutes or hours. Industrial activity can continuously alter atmospheric chemistry for years or decades. In the 2025 Earth Detecting Earth study, Sophia Sheikh and her colleagues compared several possible signs of modern technology. Their modeling suggested that Earth's present-day nitrogen dioxide signature could potentially be detected from about 5.7 light-years away, using the capabilities imagined for a future telescope similar to NASA's proposed Habitable Worlds Observatory. 5.7 light-years reaches slightly beyond Alpha Centauri, the nearest stellar system to our own, at about 4.24 light-years. The Habitable Worlds Observatory is still a future NASA flagship concept. It is intended to directly study potentially habitable planets around nearby stars and investigate their atmospheres. It should not be imagined as a telescope already operating by 2030. The 5.7 light-year result therefore describes a modeled technological capability rather than something humanity can currently perform. There is also an important problem with interpreting nitrogen dioxide. Nature can make it. Volcanic activity can influence atmospheric nitrogen chemistry. Lightning creates nitrogen oxides. Ultraviolet radiation from a star can drive chemical reactions that change the abundance of atmospheric gases. Because of this, detecting nitrogen dioxide would not by itself establish the presence of factories or machines. Astronomers would need context. They would study the host star, the planet's temperature, other gases in the atmosphere, and the chemical processes expected under those conditions. A concentration far above natural expectations could become more interesting when combined with independent evidence. This is how atmospheric technosignatures are generally treated. Their value comes from probability and consistency across multiple observations rather than one molecule, acting as a definitive label for civilization. Even so, the idea changes what technological visibility means. Human industry has altered the chemical composition of Earth's atmosphere enough that researchers can seriously model whether another civilization might eventually detect those changes across interstellar distances. And atmospheric chemistry represents only one layer of that altered planet. With a closer vantage point or more capable instruments, additional technological signatures begin to appear alongside it. The closer an observer is to Earth, the more of our technological footprint becomes available. There is no single distance at which civilization suddenly becomes obvious. Detectability works more like a ladder. At very large distances, only the strongest signals have much hope of standing out. At shorter distances, weaker effects begin to enter reach as telescopes gain enough sensitivity and angular resolution. Angular resolution describes how well an instrument can separate small details that appear close together in the sky. A distant Earth would occupy an extremely tiny angle, so features such as cities would usually blur together into the light of the entire planet. Artificial lighting is one possible clue. Modern cities release enormous amounts of visible light after sunset. Streetlights, buildings, industrial facilities, stadiums, and transportation networks create patterns that have no equivalent on an untouched planet. From space, Earth's night side can already be mapped in remarkable detail by satellites such as the Suomi National Polar Orbiting Partnership spacecraft, launched in 2011. Its instruments have recorded bright concentrations around major cities, coastlines, highways, and industrial regions. From another star, the challenge would be much harder. An observer would not see individual streetlights. It would need to detect a tiny excess of artificial illumination mixed with reflected light, atmospheric glow, and the overall brightness of the planet. Earth-level city lighting would be extremely difficult to detect, with technology comparable to ours from interstellar distances. It becomes more plausible only for a very nearby observer or a civilization with much more capable telescopes. Lasers offer a different optical signature. A powerful laser sends light in a very narrow direction. Because the beam can be concentrated, a short laser pulse may temporarily appear much brighter than ordinary surface illumination. Human astronomers already conduct optical searches for extraterrestrial technology using this idea. Instead of listening only for radio, optical searches look for very brief flashes of light that might be difficult for ordinary stellar processes to reproduce with the same timing and spectral characteristics. Some instruments are designed to detect pulses lasting billionths of a second. A directed laser from Earth would still need favorable geometry. Most observers would never cross the beam, but someone located along its path could receive a much stronger clue than someone trying to detect the glow of an entire city. Technology also changes Earth's infrared appearance. Infrared radiation is closely connected with heat. Cities frequently become warmer than nearby rural areas because concrete, asphalt, buildings, and human activity absorb and release heat differently from forests, fields, or open water. This is known as the urban heat island effect. On Earth, nighttime temperatures in large cities can remain several degrees warmer than surrounding areas under suitable conditions. Those differences slightly alter the infrared radiation leaving the planet. The Earth Detecting Earth study included effects such as urban heat islands when comparing the technological signatures of modern Earth. These are far subtler than planetary radar and would generally require a much closer observer. Human activity has also extended beyond the atmosphere. By the 2020s, Earth was surrounded by thousands of active satellites. Many thousands of additional artificial objects are tracked in orbit, including inactive spacecraft, discarded rocket stages, and fragments created by collisions or breakups. From the surface of Earth, these objects can be obvious. Ground-based tracking networks routinely follow satellites only a few meters across. Across interstellar distances, the problem changes completely. A single satellite is tiny compared with Earth. Even a dense collection of orbital hardware would normally remain unresolved, meaning a telescope would see its combined light rather than separate spacecraft. Under sufficiently favorable conditions, however, a nearby observer with advanced instruments could search for unusual periodic reflections, orbital concentrations, or other behavior associated with artificial objects. This is why satellites appear among the technosignatures considered in the 2025 study. Their relevance increases as the observer gets closer. The same pattern applies across the rest of Earth's technological footprint. Radar dominates at great distance because its strongest beams are extraordinarily powerful. Atmospheric pollution becomes interesting nearer in. Artificial lighting, localized heat, lasers, and orbital infrastructure require progressively more favorable conditions. Modern Earth, therefore, carries technological evidence across several different wavelengths and physical scales. And when researchers compared how detectable all of those signatures actually are, the gap between the weakest and strongest turned out to be enormous. The differences between these signatures become easier to understand once they are placed on the same scale. Astronomers often describe very large differences using orders of magnitude. 1 order of magnitude means a factor of 10. 2 orders means a factor of 100. A difference of 13 orders of magnitude corresponds to a factor of 10 trillion. That is the scale of variation Sophia Sheikh and her colleagues found when they compared the detectability of several technological signatures produced by modern Earth. The strongest and weakest modeled signatures were separated by 13 orders of magnitude. That means Earth does not have one simple level of technological visibility. Its detectability depends heavily on what an observer is trying to measure. Planetary radar sits at the extreme end of that comparison. The strongest intermittent radar transmissions are highly concentrated, very powerful along their beams, and produced at radio wavelengths that large antennas can detect efficiently. Under favorable assumptions, an Arecibo-like planetary radar signal could remain detectable from roughly 12,000 light-years away. Nothing else in the comparison came close. The nearest non-radio competitor had a maximum detection distance roughly 3 orders of magnitude smaller. 3 orders of magnitude means a factor of about 1,000. So in terms of maximum detection distance under the assumptions used in the study, targeted planetary radar extended roughly 1,000 times farther than the strongest modeled technological signature outside radio. That comparison refers to distance. It does not mean radar is 1,000 times more likely to be detected. A narrow radar beam may never cross a particular star system. A weaker atmospheric signature could remain present continuously for years. Observing strategy, geometry, instrument sensitivity, and timing still determine what an actual observer receives. But the scale reveals why different searches for technology can look so different. At large interstellar distances, the strongest directed radio transmissions dominate because their concentrated power can survive enormous losses. Move closer to Earth, and atmospheric chemistry begins to matter. Industrial gases such as nitrogen dioxide could become measurable if the observer has a sufficiently capable telescope and suitable viewing geometry. At still shorter distances, subtler effects enter consideration. Artificial lighting changes the planet's night side. Urban areas slightly alter infrared emission. Satellites and other orbital structures may eventually produce detectable patterns if the observer has enough resolution and sensitivity. Each effect occupies a different part of the spectrum and a different detection range. The receiving instrument matters just as much as the source. A radio telescope optimized for narrow signals will notice different evidence than an optical telescope studying reflected light. An infrared observatory examines thermal radiation. A spectrograph measures the wavelengths absorbed by atmospheric molecules. The same Earth can therefore appear almost empty to one instrument and highly unusual to another. Distance changes that picture again. An observer thousands of light-years away might have some chance of detecting a powerful radar beam if the timing and direction were favorable. An observer only a few light-years away could potentially investigate much weaker features that would disappear completely at greater distances. Time adds another layer. A technosignature must first have existed when the light or radio emission left Earth. A civilization observing our planet from 100 light-years away today receives information from roughly 1 century ago. Its view of Earth therefore contains a different technological inventory from the one we see around us now. The original question of whether another civilization could detect humanity becomes much more precise once all of these limits are included. Detect which part of humanity? With what kind of telescope? From what distance? During what period of Earth's history? And from what viewing geometry? Those details determine whether modern Earth looks silent, biologically interesting, industrial, or unmistakably technological. The framework becomes even clearer when we reverse the perspective again and look at the methods human astronomers actually use when searching for technology around other stars. Human astronomers already use many of the same clues we have imagined another civilization using against Earth. Radio remains one of the most heavily studied. A natural astronomical radio source usually emits energy across a range of frequencies. Stars, gas clouds, pulsars, and galaxies can all produce powerful radio emission, but an extremely narrow signal, occupying only a tiny slice of the radio spectrum, can attract special attention. Some searches examine features only a few hertz wide. A hertz means 1 cycle per second. For comparison, many ordinary communication channels occupy thousands or millions of hertz. Concentrating substantial energy into a frequency range only a few hertz wide can therefore produce something unusual enough to investigate. Unusual does not automatically mean artificial. Radio telescopes operate on a planet filled with transmitters. Satellites, aircraft electronics, communication systems, and radar can all produce narrow signals that enter astronomical observations. Search for extraterrestrial intelligence programs, usually shortened to SETI, therefore use additional tests. One of them involves Doppler drift. A transmitter sitting on a planet would be moving. The planet rotates around its axis, while also traveling through its orbit. Those motions continually change the transmitter's velocity relative to a distant receiver. That produces a small Doppler shift in frequency. The effect is related to the familiar change in pitch as a vehicle passes on a road. With radio, the frequency moves slightly higher or lower as the source's relative motion changes. A SETI computer can search for narrow signals whose frequencies drift over time in ways consistent with a transmitter attached to a rotating or orbiting world. Researchers still have to eliminate human interference carefully. A suspicious radio feature may disappear when the telescope moves away from the target, appear simultaneously in several unrelated directions, or match known terrestrial equipment. The process is deliberately skeptical. Light offers another search channel. Optical SETI looks for unusual laser emission from distant planetary systems. Lasers can concentrate energy into extremely narrow beams and very narrow ranges of wavelength. A sufficiently intense pulse directed toward Earth could briefly become noticeable even beside a bright star. Some optical SETI experiments search for flashes lasting only billionths of a second. The difficulty is timing. A laser pulse can pass Earth quickly, so a telescope must be observing the correct location when the light arrives. Continuous or repeatedly pulsed lasers would be easier to confirm than a single unexplained flash. Human astronomers have also used the same transit geometry that could expose Earth. In a breakthrough LISTEN study published in 2020, researchers deliberately observed 20 stars in what they called the restricted Earth transit zone. These were stars positioned so that an observer there could potentially see Earth transit across its star with especially favorable geometry. The observations used the 100-meter Green Bank telescope in West Virginia and covered radio frequencies between roughly 3.95 and 8 gigahertz. Researchers searched for narrowband signals with measurable Doppler drift. One group of signals initially survived enough filtering to receive closer attention. It came from the direction of a star, catalogued as HIP 109,656. Further analysis showed that the signals were consistent with human-made radio interference. The survey found no confirmed extraterrestrial technosignature. Its importance here lies in the observing strategy. Human astronomers deliberately targeted systems from which Earth itself would be unusually easy to discover. The reasoning is reciprocal. A civilization located there might notice our planet. making that location particularly interesting for us to monitor in return. Radio and lasers cover only part of modern SETI. Researchers also consider atmospheric chemicals that could indicate industry, unusual infrared emission associated with large amounts of energy use, and artificial compounds that natural chemistry would have difficulty maintaining. More speculative searches sometimes consider enormous engineering projects around stars, although those ideas require assumptions about technology far beyond anything humans currently possess. Across all of these methods, the underlying strategy remains similar. Astronomers search for something unusual, compare it with known natural processes and human interference, and demand repeated evidence before treating it as genuinely unexplained. That gives us a realistic model for the hypothetical observer studying Earth. It does not need science beyond recognition. Much of the basic search strategy already exists here. The growing problem is the amount of information involved. Modern radio telescopes can collect data far faster than teams of astronomers could ever examine it manually, turning the search increasingly into a problem of computation and pattern recognition. That computational problem has become large enough that modern radio astronomy increasingly depends on machines making the first pass through the data. A radio telescope does not receive a neat list of interesting signals. It records enormous streams of measurements containing natural astronomical emission, interference from human technology, electronic noise from the instrument itself, and occasional unusual events that may deserve closer study. The challenge is finding those rare events quickly enough to investigate them. The Allen Telescope Array in Northern California provides a useful example. Located at the Hat Creek Radio Observatory, it consists of 42 dishes, each about 6 meters across. The antennas can work together while observing large amounts of the radio spectrum. This produces data at rates far beyond what astronomers could examine manually. Researchers working with Breakthrough Listen, the SETI Institute, and NVIDIA have therefore been developing artificial intelligence systems capable of processing radio observations while the telescope is still collecting them. One recent system was built around NVIDIA's Holoscan platform, a computing framework designed to process continuous streams of sensor data in real time. Its first major demonstration focused on fast radio transients. A transient is simply an astronomical signal that appears for a short period rather than remaining steady. Fast radio bursts are particularly extreme examples. They can release enormous amounts of radio energy over only a few milliseconds. This demonstration was primarily a radio astronomy experiment, rather than a direct search for extraterrestrial communication. That distinction matters because the system's performance numbers describe signal processing. During testing, the artificial intelligence pipeline processed the relevant workload approximately 600 times faster than the comparison method. It operated at more than 160 times real-time speed. Its classification accuracy improved by about 7%, while false positive detections fell by roughly a factor of 10. A false positive is an event that the software identifies as interesting, even though it belongs to some unwanted or ordinary category. Reducing those mistakes matters enormously when millions or billions of measurements must be searched. The system was tested using observations of the Crab pulsar. The Crab pulsar is the rapidly rotating neutron star left behind by a supernova recorded by astronomers in the year 1054. It lies roughly 6,500 light-years away in the constellation Taurus and rotates about 30 times every second. It sometimes produces unusually intense radio flashes called giant pulses. The artificial intelligence system successfully recognized these pulses while processing radio data streams, reaching approximately 86 gigabits per second. That is more than 10 gigabytes of incoming information every second. The result does not mean artificial intelligence has made humanity 600 times more likely to discover another civilization. Its advantage is computational. Traditional pipelines often search data using predetermined mathematical procedures and then store observations for later analysis. Machine learning systems can help classify events quickly, reject large numbers of unpromising candidates, and respond while something unusual is still happening. They may also become useful for signals whose shapes do not fit the categories astronomers originally expected. That possibility matters in SETI because nobody knows exactly what an artificial extraterrestrial signal would look like. A search designed only for one narrow type of transmission could overlook something technologically produced in a form researchers had never anticipated. Real-time processing gives astronomers another advantage. If a suspicious event appears while the telescope is still observing, software can potentially trigger immediate follow-up measurements. Researchers can keep watching the same location, preserve additional data, or compare the event with observations from other instruments. The SETI Institute has continued moving in this direction at the Allen Telescope Array. In late 2025, it announced plans to integrate NVIDIA's newer IGX Thor computing platform directly into operations at Hat Creek, allowing more artificial intelligence analysis to occur close to the telescope as observations are collected. The larger trend is clear. Radio astronomy is gaining the ability to examine increasingly large portions of its data immediately, rather than waiting for lengthy offline processing. And that improvement is arriving during the same few years that much larger astronomical instruments are beginning to come online. That timing brings 2030 back into the story. 2030 is useful here as a scientific checkpoint rather than a countdown. There is no accepted prediction that humanity will detect another civilization in 2030. No telescope is scheduled to switch on that year with a known extraterrestrial signal waiting for it. The date becomes interesting because several changes in astronomy are converging within the same short period, while Earth's older transmissions continue spreading farther through space. One of the largest changes is happening in radio astronomy. The square-kilometer array is being constructed as two enormous telescope systems on different continents. SKA-Low is being built in Western Australia, on Wajari Yamaji country at the Murchison Radio Astronomy Observatory. Instead of using conventional dishes, it will contain large numbers of relatively small antennas designed to observe lower radio frequencies. SKA-Mid is being constructed in South Africa's Karoo region. It uses dish antennas and will operate at higher frequencies. The two facilities are being assembled gradually rather than appearing all at once. Under the current scientific schedule, an early stage of science verification for SKA-Low is planned for the first half of 2027. Science verification means astronomers begin testing whether the telescope can perform real scientific observations and produce reliable data. A corresponding early science verification stage for SKA-Mid is planned around 2029. More complete versions of the arrays follow later. SKA-Low is currently expected to reach another major science verification stage around 2029, with its first shared risk observing cycle beginning around 2030. Shared risk observing means outside astronomers can propose real projects while the telescope is still moving toward routine operations. Because the system is still being commissioned, an observation that fails may not automatically be repeated. SKA-Mid currently follows on a later schedule, with a more complete science verification stage around 2031, and its first shared risk cycle around 2032. Projects this large can shift by months or years as construction and commissioning continue, so those dates should be treated as current plans. The importance of the square kilometer array comes from collecting area, sensitivity, and scale. Radio astronomy becomes more powerful when an instrument can gather extremely faint signals and survey large amounts of sky efficiently. That same stream of astronomical data can potentially support technosignature searches. One useful approach is called commensal observing. In a commensal search, a telescope can perform its main astronomy project while additional software examines the same data for signals that might interest SETI researchers. The telescope does not necessarily need to spend a separate night searching only for technology. Optical astronomy is approaching its own major milestone. On Cerro Armazones in Chile's Atacama Desert, the European Southern Observatory is building the extremely large telescope. Its main mirror will be approximately 39 meters across. A single glass mirror that large would be extraordinarily difficult to manufacture and control, so the surface is divided into 798 hexagonal mirror segments. Computers and sensors will keep those pieces aligned closely enough to behave as one enormous reflecting surface. The observatory sits more than 3,000 meters above sea level, where the dry Atacama atmosphere provides excellent conditions for infrared and visible light astronomy. The current schedule places telescope first light in March of 2029. First light means the completed telescope begins making its initial test observations. After that comes installation and commissioning of scientific instruments. The first scientific observations are currently expected in December of 2030. Among the extremely large telescope's major objectives is the study of exoplanets, including the atmospheres and physical properties of potentially habitable worlds. So, while Earth's technological signals continue moving outward, our ability to investigate other planetary systems is improving at the same time. From 2026 to 2030, every radio wave, already traveling away from Earth, gains 4 additional light-years of distance. A transmission from 1960 moves from roughly 66 light-years away to roughly 70. During those same 4 years, new radio arrays, giant optical telescopes, and increasingly powerful computing systems move closer to routine scientific use. The two processes follow completely different schedules. Light expands Earth's historical reach at exactly 1 light-year per year. Telescope capability advances through engineering, construction, and improvements in computing. By 2030, humanity will therefore occupy a slightly larger detectable volume, while possessing better tools for examining the worlds around us. Those better tools will almost certainly reveal strange things. The harder task begins afterward, because astronomy has repeatedly shown that discovering an anomaly is much easier than proving what produced it. Greater sensitivity will inevitably produce more unusual detections. The difficult part is deciding what those detections actually mean. In astronomy, an interesting anomaly sits near the beginning of the process. A signal or atmospheric feature may look unusual enough to deserve attention, but it becomes a candidate technosignature only after researchers begin ruling out ordinary explanations. The standard becomes progressively stricter from there. Scientists try to observe the feature again. Other instruments may be asked to confirm it independently. Natural processes, equipment problems, and human-made interference have to be tested carefully. Only after those alternatives become increasingly difficult to maintain would a technological explanation begin to look compelling. Radio astronomy shows why this caution is necessary. Earth is surrounded by transmitters. Communication satellites cross the sky constantly. Navigation systems, radar installations, aircraft electronics, and ground-based communication networks can all leak energy into radio telescopes. A narrow radio feature may therefore look interesting at first and still originate only a few hundred or a few thousand kilometers away. Astronomers use several checks to separate local interference from something genuinely associated with a distant star. One simple test is to move the telescope slightly away from the target. If the signal remains equally strong when the telescope points somewhere else, that suggests the source may be local interference entering the instrument from the side. A genuinely astronomical signal should normally behave consistently with the telescope's changing direction. Independent observatories provide a much stronger test. If a telescope in West Virginia detects something unusual, an observatory hundreds or thousands of kilometers away can attempt to observe the same sky position. A signal appearing at multiple separated sites, with timing and frequency behavior consistent with a distant source, becomes much harder to explain as a local transmitter. Repetition matters for the same reason. A single unexplained event can remain ambiguous for decades. A signal that returns from the same stellar system gives researchers much more information. They can compare its frequency, duration, intensity, and timing across multiple observations. Small frequency changes can also help. A transmitter attached to a rotating or orbiting planet would change velocity relative to Earth. That motion can produce the Doppler drift discussed earlier, causing the observed radio frequency to slide gradually over time. If repeated signals show a drift pattern consistent with motion inside a distant planetary system, that adds another independent piece of evidence. Atmospheric technosignatures require the same kind of restraint. Nitrogen dioxide can be associated with combustion, but natural chemistry can produce it too. Oxygen can accumulate through biological activity, while certain non-biological processes can also create large amounts under particular planetary conditions. Methane has important biological sources on Earth, yet geological processes such as reactions between water and certain rocks can also generate it. An astronomer studying another world would therefore build a larger environmental picture. The temperature of the planet matters. The type and activity of its star matter. Other atmospheric gases can reveal which chemical pathways are plausible. A single unusual molecule might remain interesting without becoming decisive. The strongest observational case would come from several independent clues pointing toward the same interpretation. Imagine finding an Earth-sized planet transiting a nearby star once every year or two. Its atmosphere shows chemistry consistent with an active biosphere. Additional observations reveal an atmospheric compound present at concentrations difficult to reproduce with the natural processes modeled for that planet. Later, a narrow radio transmission appears from the same stellar system and is detected repeatedly. If optical or thermal observations then reveal further unusual behavior, the combined case becomes much stronger than any one detection could provide. Each clue tests the others. The planet establishes a physical location. Atmospheric measurements describe its environment. Radio observations introduce evidence that may be difficult to generate without technology. That is the standard hidden inside the simple phrase, "finding another civilization." A convincing discovery would probably emerge through accumulation rather than one dramatic moment. And the same would apply to someone studying Earth. To see what that process might actually look like, we can now place a hypothetical observer only a few tens of light years away, and give it technology roughly comparable to our own. Imagine a civilization somewhere between 10 and 30 light years from Earth. We do not need to place it on any real planet. Give it telescopes roughly comparable to ours, perhaps somewhat better, and position its system inside the narrow Earth transit zone. From that location, Earth would pass across the face of its star once every year. At first, the civilization might know almost nothing about the planet. A sensitive telescope would record a tiny reduction in starlight, only about 84 parts per million. The event would repeat after roughly 365 days. After several years, the pattern would become difficult to dismiss. The timing would establish a stable orbital period. The depth of the transit would suggest that the object crossing the star had a radius roughly similar to Earth's. Additional measurements of the star and the duration of each transit would help constrain the orbit. At this stage, Earth would be a line in a catalogue, a roughly terrestrial planet. 1 year orbit, suitable distance from its star for further investigation. More capable instruments could begin studying the atmosphere. During each transit, a tiny amount of starlight would pass through the gases surrounding Earth. Spectroscopy could search that light for water vapor, carbon dioxide, oxygen, ozone, methane, and other molecules. Those gases would provide environmental information rather than a simple declaration of life. Water vapor could suggest an atmosphere capable of supporting a water cycle. Carbon dioxide would help reveal greenhouse conditions. Oxygen and ozone could become biologically interesting when considered alongside the rest of the atmospheric chemistry. Methane would add another clue because it is chemically unstable in an oxygen-rich atmosphere and must be replenished. A cautious observer would still keep several natural explanations open. But after enough atmospheric measurements, Earth might begin to look like a planet where active biological processes were worth serious consideration. Then the technological era would begin reaching them. Suppose this civilization is 20 light years away. Everything it observes about Earth is delayed by 20 years. In 2030, it sees Earth approximately as it was in 2010. Radio signals emitted in 1960 would have passed its location around 1980. A transmission from 1974 would arrive around 1994. Later, radar and deep space communication beams would cross that distance according to the dates they were transmitted and whether their directions happened to intersect the system. Most ordinary radio leakage could be far too weak to identify. A favorable encounter with a powerful radar beam would be very different. If the civilization happened to lie inside the main beam of an intense planetary radar transmission, its instruments could receive a concentrated radio signal far stronger than the faint atmospheric clues it had spent years measuring. The signal might be narrow in frequency. It could show changes produced by Earth's rotation and orbital motion. Its direction would point back toward the same planetary system where a small rocky world had already been observed crossing its star. A careful scientific community would probably avoid announcing a technological civilization after one event. They could keep watching. Later transmissions might appear from approximately the same location. Deep space communication could produce additional narrow beams as humans contacted spacecraft around different planets. Repeated artificial-looking radio features would make coincidence and natural explanations increasingly difficult to maintain. If the observer possessed better atmospheric instruments, it might eventually notice changes associated with industrial activity. Nitrogen dioxide could become one candidate. Other technologies might leave optical or infrared effects that were individually weak but useful when combined with stronger evidence. The recognition of humanity would therefore have no required single moment. It could begin with a small annual dip in starlight, develop into years of atmospheric study, and become far more significant when artificial electromagnetic activity finally reached the same observatory. The researchers there might move gradually from knowing that Earth exists, to suspecting that Earth has life, to concluding that something on the planet uses technology. By 2030, the important issue is how far that sequence could realistically have progressed. The date gives us a specific boundary for comparing Earth's expanding signals with the distances over which a response could already have begun traveling back. By 2030, the physical boundary around Earth's technological history will have moved 4 light-years farther outward than it is in 2026. That expansion happens automatically. Radio, radar, television leakage, spacecraft commands, and every other electromagnetic signal already traveling through space continue moving at the speed of light. Nothing needs to be transmitted again for those existing wavefronts to reach new locations. 4 light-years can sound small against the scale of the Milky Way. Within the immediate stellar neighborhood, though, 4 light-years is a meaningful distance. The nearest star system to Earth, Alpha Centauri, is only about 4.24 light-years away. Moving a signal boundary outward by 4 light-years can therefore carry a particular period of Earth's technological history across additional nearby stellar systems. The oldest radio experiments provide the outer edge. Signals escaping Earth around 1895 will have had about 135 years to travel by 2030. Their maximum physical distance from Earth will therefore be roughly 135 light-years. Signals from 1960 will have traveled approximately 70 light-years. The famous Arecibo message transmitted in 1974 will be about 56 light-years away. Those numbers describe where electromagnetic energy could have arrived. They do not tell us whether a receiver there could detect it. The 1895 wavefront may be the farthest out, while its weak early emissions are among the hardest to identify. Later, planetary radar can be dramatically more detectable along the correct beam, even though those transmissions occupy a smaller volume because they were sent much more recently. The timing becomes especially interesting inside the nearest few dozen light-years. A transmission leaving Earth in 1960 has 70 years available before 2030. Under an idealized scenario, 35 years could be spent traveling outward and 35 years returning. That means an observer roughly 35 light-years away or closer could physically receive a 1960 signal and send an immediate electromagnetic response that reaches Earth by 2030. For something transmitted in 1974, the corresponding limit is about 28 light-years. Real boundaries would usually be smaller. A civilization would need time to detect the signal, establish that it was unusual, determine where it came from, and decide whether to respond. The original transmission would also need enough strength and favorable geometry to be noticed in the first place. Meanwhile, Earth's technological footprint is still changing. NASA continues transmitting commands towards spacecraft through the Deep Space Network. Planetary radar did not end with Arecibo's collapse. Facilities including the Goldstone Solar System radar in California continue using powerful radio transmissions to study asteroids and other objects. Thousands of active satellites circle Earth, while industry continues altering atmospheric chemistry and the thermal and optical appearance of populated regions. So, an observer receiving Earth in 2030 would be receiving a different technological planet depending on its distance. Someone 20 light-years away would see electromagnetic information from approximately 2010. At 50 light-years, the observable Earth would correspond roughly to 1980. At 100 light-years, the arriving information would describe Earth around 1930. Human technology continues changing here, while different historical versions of that technology spread outward at light speed. Our own ability to search is changing much faster. Artificial intelligence systems are beginning to process enormous radio datasets close to real time. The Square Kilometre Array is entering scientific use in stages, with SKA-LO currently expected to begin its first shared risk observing cycle around 2030. In Chile, the extremely large telescope is currently scheduled for telescope first light in March of 2029, followed by its first scientific observations around December of 2030. None of these dates guarantees a discovery. Together, they make 2030 a useful snapshot. By then, Earth's signals will have reached farther into the nearby stellar population, while human astronomers possess more sensitive instruments and faster methods for recognizing unusual information coming the other way. Nothing special happens when the calendar turns to January 1st, 2030. The important possibility is that, from somewhere else's perspective, the meaningful threshold may have been crossed years earlier. There is currently no confirmed evidence that another civilization has detected Earth. There is also no scientific basis for predicting that such a discovery will occur specifically by 2030. What modern astronomy can do is define the conditions under which discovery becomes physically possible. The first layer is simply the existence of Earth. From the right viewing geometry, a distant observer could detect the planet through the small reduction in starlight that occurs once every year. Repeated transits could reveal its orbital period and approximate size. With better instruments, the atmosphere becomes available for study. Oxygen, ozone, methane, water vapor, carbon dioxide, and other gases could reveal information about the planet's environment. Certain combinations might suggest active biological processes, although natural explanations would still need to be examined carefully. Technology adds a newer set of clues. Radio and radar can travel directly across interstellar space. Industrial chemistry can alter atmospheric composition. Powerful lasers can produce concentrated optical signals. Artificial lighting, heat from cities, and orbital infrastructure become possible signatures at progressively shorter ranges or with increasingly capable instruments. But the existence of a technosignature is only the beginning. The information must first have enough time to reach another system. Then, a receiver must be sensitive enough to detect it under the actual observing conditions. Geometry can determine whether a powerful narrow beam crosses the system at all. After detection comes interpretation. A strange radio feature could be natural emission or interference. An unusual atmospheric molecule could have a geological or chemical source. Convincing evidence would require repeated observations and several clues that reinforce the same explanation. And if someone chose to answer, the reply would begin another interstellar journey governed by exactly the same speed limit. This distinction helps explain the most surprising number in the entire story. Under the assumptions used in the Earth Detecting Earth study, a powerful Arecibo-like planetary radar signal could theoretically remain recognizable from roughly 12,000 light-years away, with comparable receiving technology and favorable geometry. 12,000 light-years is an enormous detection range. Yet humanity has not been producing those signals for 12,000 years. Our modern technological emissions have existed for decades, or, in the case of the earliest radio experiments, a little more than a century. So the distance at which a signal could eventually be detected and the distance it has actually reached today can differ by thousands of light years. The same separation appears closer to Earth. The historical Earth Transit Zone study identified real stellar systems that have occupied positions from which our planet could cross its star. By the time that work was published in 2021, human-made radio waves had already passed 75 of the closest stars in that sample. NASA's Deep Space Network adds another layer. Its transmissions do not scatter randomly across the sky. They follow spacecraft and planetary geometry, producing radio paths that are especially common near parts of the sky associated with planetary orbits and Earth transit viewing positions. None of this tells us that anyone was there. It tells us that the geometry and travel time required for detection already exist in some nearby directions. Consider a hypothetical civilization 20 light-years away. If it received an unmistakably artificial signal from Earth, that detection could already have occurred according to our calendar. Earth would receive no notification that the event had happened. The astronomers there could publish papers, repeat observations, debate the evidence, and eventually conclude that a technological species existed here while humanity remained completely unaware of their discovery. If they transmitted a response, that message would then require another 20 years to cross the distance. During all of that time, both civilizations would occupy the same galaxy while possessing completely different information about each other. That is the quiet consequence of interstellar distance. Humanity continues listening outward with larger telescopes, faster computers, and increasingly sensitive instruments. Meanwhile, Earth's own history continues traveling in the opposite direction. Every year, the oldest emissions move another light-year farther away. Later, radar and communication beams follow behind them, carrying increasingly recognizable evidence that something technological appeared on this planet. Somewhere beyond Earth, the answer to whether humanity has already been found could therefore exist before the answer has any way to reach us.